Welcome back to the classroom. Everyone, today in the lecture 9, we address an important engineering problem that emerged in our previous discussion. In the last lecture, we studied the single beam spectrophotometer and we discovered a fundamental limitations. The accuracy of the instrument depends entirely on a perfectly stable light source. During measurement, we manually sap the reference cell and sample cell. Even a tiny fluctuation in lab intensity during this short interval invalidates the absorption data. This is not a minor inconvenience, it is a fundamental physical weakness. To overcome this limitation, optical physicists developed double beam spectrophotometers. The key idea is elegant. Instead of measuring sequentially, we measure reference and sample simultaneously or nearby simultaneously. The incident light is divided into two optical paths. This allows continuous comparison between the analyte and the reference blank. Today, we will study two major architectures, double beam in space, double beam in time. Both designs begin similarly. A continuous light source passes through a monochromator and then sophisticated optics manipulate the beam. Let us begin with the spatial configuration. Observe the schematic carefully. Let us trace the journey of light. Radiation originates from the source and enters the monochromator. The monochromator selects a narrow wavelength band. After exiting, the beam encounters a beam splitter. This component divides the radiation into two independent beams. Unlike the single beam design, both beams exist at the same time. One beam passes through the sample cell, the other beam passes through the sample cell. These beams travel along separate spatial paths. After interaction with the cells, each beam strikes its own photodetector. We now have photodetector 1 for reference signal and photodetector 2 for sample signal. The electrical outputs are sent to a difference amplifier. The system continuously compares the two signals and directly computes transmittance or absorbance. Source fluctuations are automatically cancelled. At first glance, this seems like the perfect solution, but physics always introduces trade-offs. Let us analyze the mechanism deeper. A V-shaped beam splitter creates two beams. Beam 1 forms the baseline, beam 2 measures the analyte. Electronic circuitry calculates the signal ratio continuously. Any instantaneous lamp fluctuations affects both beams equally, therefore it cancels mathematically. However, a severe limitations appears. The system requires perfectly matched detectors. Both detectors must have identical quantum efficiency, identical noise characteristics, identical aging behavior. In reality, manufacturing two perfectly identical detectors is nearly impossible. Even if matched initially, they drift differently over time. Calibration becomes difficult, long-term accuracy suffers. Engineers therefore search for a superior design. This led to the most widely used architecture in modern spectroscopy. The solution is brilliant. Instead of two detectors, use one detector. Light again exit the monochromator, but now it meets a motorized sector mirror. This mirror rapidly alters the beam direction. First, the beam passes through reference cell and milliseconds later through the sample cell. Both signals reach the same photodetector. Because measurement occur within milliseconds, any slow drift in lamp intensity becomes negligible. The detector response remains identical for both measurements. The resulting signal is amplified and displayed. This architecture eliminates the matched detector problem entirely. Let us examine the rotating sector mirror. The mirror contains pie-shaped segments. Half the segments are reflective, they are direct light toward the reference path. The remaining segments are transparent, they allow light to pass toward the sample. Between segments are blackened frames. As the mirror rotates, these frames temporarily block light. During these brief interruptions, the detector measures its own thermal noise. This provides automatic dark current correction. After passing through the cells, a grid mirror recombines the pulse beam. Major advantages include single detector operation, automatic baseline correction, and improved long-term stability. This is why double beam in time systems dominate modern instruments. Let us summarize why double beam instruments are preferred. First, they compensate automatically for source instability. Second reason is that they correct detector and amplifier drift in a real time. Third reason is that they compensate for wavelength dependent lamp intensity variations. Remember, deuterium lamps dominate UV, tungsten lamp dominate visible region. The ratio measurement neutralizes these variations. And fourth reason is that they allow continuous spectral scanning. We can record absorbance as a function of wavelength in a real time. Finally, operation becomes simpler, no manual calibration steps, no repeated blank measurements are needed. The instrument directly displays the absorbance instantly. Let us compare both architectures. In double beam, in space requires two matched detectors, calibration complexity is high, dark current correction often manual and less common today, whereas double beam in time uses a single detector, calibration is simpler, dark current correction automatic, preferred in modern spectrometers. With this, we conclude our discussion on instrument in architecture. Now we shift focus completely from hardware to chemistry inside the cuvette. Thank you.